So what we learned from the last set of videos was about work and energy, and how we can store energy and how energy manifests itself. So when we think about the way energy looks or the way it manifests, the energy of motion we call kinetic energy. And if you want to solve for the kinetic energy of an object, use this 1/2 mv squared, where m is the mass and v is the speed. If you want to figure out how much elastic energy is stored in a spring or a rubber band, we call that elastic potential energy. We use U for potential energy and S for spring, and that's equal to ½ kx squared, where k is the spring constant and x is either the stretch distance or the compression distance, depending on whether you're stretching or compressing a spring. We also realize you can store energy in a gravitational field. We call that gravitational potential energy. It's mgh, where m is the mass, g is the gravitational field strength, and h is the height above a reference point. Oftentimes we use the ground for the reference point. It doesn't have to be the reference point. We can actually use any point, and then we just measure the height up from there. So here's our 3 basic ideas. In general, we talk about work. The work is equal to the force times the distance. In a specific way, it's not just the force times the distance, it's the force vector dot the distance vector. And so we only want the parts of those that are parallel, so we might have to use the dot product or figure out the cosine or something like that. And when in a very specific case, if we have an object sliding with friction, right, we can get the work done by friction, but that is a specific case. So here's our concept. So let's see, first of all, how these two can work together. So we're going to use a construct that we use all the time in physics. And we'll go with a frictionless surface. And on this frictionless surface we have a box, and this box is free to move left and right. The cool thing about this is that there's no friction, but this is a great spring because it has compression and stretchability here. And so if I were to take this box and pull it out here and let it go, it would slide back and come to a stop, then slide out and come to a stop, and back and come to a stop, and out and come to a stop. And when I look at that situation, it's going to go back and forth, and this is a war, right? This is a war between the elastic potential energy and the kinetic energy. So we call this right here, we call this the equilibrium position because the spring is neither stretched nor compressed. If I were to take this box and push it in and compress the spring and then let it go, it might look like this. So that's where I'm going to let it go. And then it's going to slide out. So this is the equilibrium position. This is the compression. This is the stretch. One of the ways that we analyze the energy of a system is we can use energy bar charts, for example. So I'm going to pull this in and let it go, and it's going to slide out and then slide back and slide out and slide back. So if I let it go at A, it's going to slide through B and come to a stop at C and then slide back. So let's look what the energy looks like here. So I think about the energy situation. If I pull it back to A and I let it go, it's not moving at all. So all my energy would be elastic. As it slides through B, it's moving fast. So all my energy would be kinetic. And then as it comes to C, again, it slides to a stop at C. But what do we notice in all three of these situations? The total amount of energy is the same. And so we just have a transfer of energy there and back, there and back. And so we have a rule for this. It's called the law of conservation of energy, and that means that the total amount of energy stays the same. So we can say that the initial energy, for example, is equal to the final amount of energy. And that's one way to express this. So if we take this one specifically, between A and B, what I've done is I have compressed the spring a distance x. Our box has a mass m, spring constant k. And so what we can say is, if I look at between A and B, how do these two things compare? Well, if the total amount of energy is constant, the E final is equal to the E initial. I can say that the total amount of energy at A is equal to the energy at B. Well, how do I represent the energy at A? All the energy is in the spring. And what about the energy at B? It's all kinetic energy. If I go to plug and chug values now, or not values, I'm going to put the letters in. This is 1/2 kx squared is equal to 1/2 mv squared. So this allows me to compare the spring constant, the compression distance, the mass, and the speed. And it just gives us a general construct to understand how those things work together. Now, this is a little easier because it's a frictionless situation. So we know the total amount of energy before is equal to the total amount of energy after. If this were a friction situation, we can totally do that. But what we'd have to add, if we put in a coefficient of friction here, we'd have to say that the energy at A is still equal to the energy at B. However, we have the total amount of elastic energy to start is equal to the kinetic energy plus what we know is that as this rubs against the ground here, as it slides this way from here to here, there's some rubbing between the two surfaces. This rubbing creates what we call thermal energy. This thermal energy heats the blocks and heats the surroundings, and so we realize this as a temperature change. But this thermal energy, you can't stay in there because it just makes everything hot, and then this heat energy, this thermal energy, is released to the surroundings, released to the surrounding air and the surrounding bodies. So we call this thermal energy. The thing about this that's really cool is that this thermal energy is also the work done by friction. So it's this frictional force. So the work done is the force times the distance. So this work done by friction is the frictional force times the slide distance. And we could go a little further with this. We don't need to solve it specifically, but we're getting a sense of how these things relate. Another way that this type of problem manifests itself this time we're going to put a box on a hill. And we're going to put a box on a hill here. We're going to look at it partial the way down the hill. And we'll look at it down here. Now, just in our brains, if you release a box from rest here, we'll say that the whole thing is frictionless for now. As it slides down here, it's obviously falling down, so we know there's a decrease in the gravitational energy, but it's speeding up, so there's an increase in the kinetic energy. But, again, the law of conservation of energy applies, which means the total amount of energy in the system has to stay the same. So what does that look like for our bar charts this time? So this time we have gravitational potential energy and kinetic energy. So what's our situation? At the very top here, it has all gravitational energy, but it's not moving, so no kinetic energy. Down here at the bottom, it's gotten all the way down, so it doesn't have no gravitational energy at all. But it has kinetic energy. But over here, it's part of the way down, and it's still moving. So I like this one. So it has a little bit of both. But if we look at the size, this is equal to these two, which is equal to this one. The total amount of energy stays the same. So how does that manifest? We call these points A, B.
Good afternoon, Norseman. I am happy to inform you in some cases, but in others I know that you'll be sad to hear that tomorrow we are not having school in Grosse Pointe Public Schools. I hope that you stay safe, stay warm. Please know that all afternoon activities are canceled as well. Be safe on the way home. Thank you.
That was awkward. So we look at here, and we see that the total amount of energy stays the same. We'll call these A, B, and C. So if we just compare, let's say A and C, for example, the initial energy has to equal the final energy. So in this case, it's the energy at A has to be equal to the energy at C. No big deal. I know at A, it's all gravitational energy. At C, it's all kinetic energy. So if I plug and chug this, mgh is equal to 1/2 mv squared. Now, what h are they talking about here? Well, the thing about the h is that it has to be from some reference level. So we have to decide where h equals 0 is. In most of these problems, there's a ground level. We're going to call this h equals 0 here, so that now I can say that that distance is h. And that's a fine way to do it, but in all these problems, whether it's implied or not, you should designate where your h equals 0 is, because it's much easier that way. What I like about this problem is this now gives me a sense of how to relate the speed at the bottom to the height that it was released from. But there's a sneaky thing in here, and the question is, If I put a block that was twice as massive here, how would the speed at the bottom differ? It's a great question, right? Well, what I notice is that because there's an M on the left side and an M on the right side, we could Harry Potter these things away, and we realize that the speed here is really interesting because it only relies on the height. The actual mass doesn't matter, which is kind of a great thing. So that's one way to work with the gravitational energy here. If we look at from